Okay, guys, we're in advanced math, mod 7. Today is Tuesday, April 28th. Again, Tuesday, April 28th. So, taking your notes here today, top left of your corner of your paper, go ahead and put 4/28/20. Tuesday, 4/28/20. The title of the notes, Exponential Growth and Decay. Finally, we're going to show you some real life uses for the exponential and logarithmic equations that we've been working with and learning how to solve. And guys, this is a real important growth formula. I don't know if you've been introduced to it before, whether it be last year in Algebra 2 or even in a science class. But this is the world-renowned, accepted growth formula that basically you can calculate the rate at which something is growing. For example, let's say you thought you maybe had strep throat and you went to the doctor and they swabbed your throat and took what's called a throat culture. Okay, there's no magic pill they have that determines, oh, here's what that is. They basically allow that group, that culture of germs or bacteria or virus, sit around for several minutes, okay, an hour or two if need be, whatever, and see the rate at which it's multiplying or growing. And how fast it's multiplying or growing will help determine what kind of virus, germ, bacteria it is. And once they determine what kind it is based on how fast it's growing, because they all grow at different rates, then of course they can look at a chart and decide what antibiotic is used to take care of it and kill it and make it disappear. So this is a growth formula or decay formula used for bacteria, germs, viruses, anything that grows. Could be your hair, your fingernails, or something that decays, okay, like a dead body or your teeth, or anything that's getting smaller because it's decaying rather than growing. The growth rate or the rate of decay can be calculated by good old y equals b times e to the kt. So the title of the notes, Exponential Growth and Decay, and in a box with a star next to it, this has got to be memorized, y equals b times e to the kt, which means nothing to you, of course, unless you know what all those letters represent or stand for. So real quick, first note off to the side, let's make a little note about what each letter is going to stand for. Okay, so again, this is just something that's sitting here. Time is going to pass, and this is going to, it could be population growth, could be the growth of the stock market or the economy, which in this case would be decaying, right? So here we go. Y, like any other function we work with, is going to be what? The output value at the end. So the Y value will, of course, always be the final amount of material that's sitting there at the end of the experiment, whether it's number of people, the amount of germs, the amount of bacteria, the amount of money. It's the final amount of the thing that's growing. B is the letter B because it's the beginning amount of material. I guess we could also call that the original amount that you started with, correct? K is the all-important rate of growth. Now, technically, they don't call it the rate of decay. They call it the rate of growth. If it's growing but getting smaller and smaller, in other words, it's decaying, that just means the growth rate will be a negative number. Agreed? It's growing at a negative rate. And T, of course, is the amount of time that the stuff we're looking at, whether it be money, population, germs, bacteria, whatever, how much time that it's been sitting there and growing, or in some cases, like I said, decaying. Okay? So with all that in mind, that kind of makes the formula self-explanatory. Let's look at a couple examples. Example 1. Right now, let's say we did take a throat culture, a sample of a group of viruses or germs or bacteria, and there were 2,000 milligrams of something. We let it sit around for 6 hours. Whoa, and after 6 hours, it grew and multiplied and got more and more of it, and it grew to 6,000 milligrams of material. And we simply want to know, big star, what's the growth rate of that material? So if you go to the doctor, he takes a throat culture, he swabs 2,000 milligrams of stuff, and 6 hours later, oh my gosh, there's 6,000 milligrams of that stuff. There's only one type of material, virus, bacteria, germ, whatever you want to call it, that grows at that rate. Okay, if it's a known value, a known virus or a known bacteria. So what is the growth rate of that object or that material? Okay, well guys, we've got everything we need to stick into that formula. Watch how easy. Y is the final amount of material. Oh, well remember, 6 hours after we started this experiment, there were 6,000 milligrams of material sitting there. Agreed? That's what it grew to. So Y, my final amount is 6,000, equals B is the beginning amount. Well, remember, we started with 2,000 times E to the K is the rate of growth. We don't know that, do we? That's what we're seeking. So that's our K, our unknown. And T is the amount of time it's been going on, the experiment. We let it sit there for 6 hours and grow and grow and grow. So 6 times K is our exponent. Now, obviously, guys, if we want to know what's the growth rate, we're seeking to solve for the letter K, aren't we? And it's an exponent. But there's a dot connected 2,000 here. So let's calmly think about the best way to attack this equation. You agree we would divide divide both sides by 2,000? Why not get rid of that 2,000? We're trying to isolate the K. So really, 6,000 divided by 2,000, I don't need a calculator. I get 3 equals E to the, doesn't that look nicer if you write 6K? Now, if I said, okay, everybody, go ahead and finish that now, get K by itself, I hope no one would be stuck. Think about it. What would you do if your job was now to solve for K and get K by itself? Well, isn't that what we just spent 2, 3, 4 days on, solving exponential equations? When in doubt, log it out. Every time you're solving an equation with a missing exponent, you're supposed to log both sides. Since there's an E involved in this formula, of course, we're going to ln. We're going to natural log both sides. So I've got ln of 3 equals the ln of E to the 6K. I said it, but I didn't write it because that 6K is going to get moved to the front, isn't it? Remember the power rule? I always put it in front of the log. And if you remember correctly from what, 2, 3 days ago, ln E, if you ever see it, is irrelevant because it's really the number 1, isn't it? So if it's a 1, I can ignore it. So bottom line is, for me to solve for K, I divide by 6. It was easy. The 6's cancel, and K equals, now pull out your calculator. My advice has always been what? Type the top in first. ln 3, hit enter, divided by 6, enter. Nearest 3 places, we've got 0.183. Now careful, don't circle that. Look up your definition. K is the rate of growth. Oh, I want to know the percentage that it's growing each hour. So technically, you always move that decimal 2 to the right, giving me 18.3% per what? Hour since. Oh, that bacteria, that virus, that whatever it was sitting for 6 hours. It's growing at a rate of 18.3% per hour. Cool. So that chemist working at the doctor's office in the research lab, when he's gets a culture of something and has to decide, well, what is this stuff? He basically, or she, figures out the rate at which it's growing by using this formula. So thank God you paid attention when you learned how to solve exponential equations. Okay? Interesting. So putting a little science twist on your math skills here. Example number 2. 17 years ago, Mr. DeMarco's hair weighed 275 milligrams. Now, unfortunately, it's decaying and dwindling away. His hair only weighs 80 milligrams. Now it's the same length that it was. He just doesn't have as much, obviously, right? So what's the rate of decay? Now I can use the word decay, even though I also could have said, what's the growth rate? I knew it was a decay problem because what? He started out 17 years ago with 275 milligrams of hair. Now, 17 years later, it only weighs 80 milligrams. So it weighs less now than it did at the beginning. So back to using our formula. Y, the final amount is actually how much hair he has now, right? 80 equals the beginning amount of hair 17 years ago. There were 275 milligrams times e to the, I don't know the rate, the growth rate, do I? That's my unknown k. And time was what, 17 years ago. I'm going to put 17. That just means when I label my answer, it's going to be a certain percentage per year instead of per hour. Agreed? Now, just like that last problem, don't get stuck at this point. You're dividing by that 275. Why not get rid of that number? It's not needed over here on the right side. Get rid of it. So I'm pushing on my calculator. Hold on a second. 80 divided by 275 and getting 0.291 equals e to the 17k. Agreed? Oh, I'm looking for a missing exponent again. Let's ln both sides. ln of 0.291 equals ln of e to the 17k. That goes out in front. The ln e is irrelevant because it's a 1. To get k by itself, I divide by 17. And k equals, okay, on my calculator, I'm hitting ln of 0.291. Enter. Divided by 17. Enter. Negative 0.073. So, if I move that again 2 to the right, technically, to get the right answer here, my growth rate, his hair is growing at a rate of negative 7.3% per year. So really, the decay rate is 7.3%. The growth rate, would be negative 7.3 because it's growing backwards and getting smaller. Okay? Finally, last example and we're done. You're doing great. Hang in there. Ooh, what if instead of a material, we're talking about population? So let's look at the Louisville population. So we're talking about the number of people instead of the number of germs or the amount of hair. Let's say in 1995, Louisville had 5,685 people. I'm just making these numbers up. And in 2004, so that's what, 9 years later, there were 6,376 people. And we were able to do a little experiment and look at these populations and prove that the Louisville population was growing at an exponential rate. We want to predict when will, if it hasn't already, or when did the population finally reach 6,800 people. We're trying to make a prediction. That's why you see a lot of this stuff used in statistics with exponential growth and decay, right? Because we're trying to predict an outcome of an experiment. When's this going to happen? Okay, so statistically speaking, if you studied these statistics, when will the population reach 6,800 people? So make sure you got that problem written in your notes. Now, this isn't as straightforward as the last two that we did, right? Think about this for a minute. Let's go ahead and write down our equation again. Make sure you got it. Y equals B times E to the KT. Now, careful. In the beginning of this experiment, there were 5,685 people, right? And at the end of this experiment, there were in the year 2004, there were 6,376 people. So I'm not predicting yet. I'm just looking at those statistics. I've got a beginning amount and a final amount, don't I? So my final amount of people in this little 9-year experiment is 6376 equals, in the beginning of this problem, there were 5,685 people, times e to the k is unknown, and t, think about it, we started in 95, we finally looked in 2004, so didn't 9 years pass by? So just like those last two, we can at least solve for k now, correct? Divide by 5685 on both sides. Stay with me, think with me. Those cancel. I'm pushing 6376 divided by 5685. I'm getting 1.122 to the nearest three places equals e to the what? 9k. I'm looking for a missing exponent, aren't I? So I'm going to log both sides. When in doubt, log it out. Because there's an e, I'm going to ln both sides. ln of 1.122 equals 9k ln e. Agreed? ln e is gone. I divide by the 9. And my k value is, I'm pushing ln of 1.122, enter, divided by 9, and getting to the nearest, looks like 0.01279. We might as well get as specific as we can. Now, guys, don't circle that. I didn't say what's the growth rate from 1995 to 2004. What's the growth rate? I didn't say that. I want you to make a prediction as to when the population will reach 6,800 people. When? How many years is it going to take? Oh, so now, watch this. Going back to our formula again, the final amount of people now is what? 6,800, isn't it? When are we going to reach that many people? I want the final total of people to be 6,800 for my population. So 6,800 equals, now, at the beginning of the problem, there were still, what? 5,685 people times e to the, interesting. We now have a k value to plug in, don't we? We figured out the rate it was growing. So I can put that 0.01279 up there for k times t. The amount of time it's going to take to get that many people is what's unknown. So now when I divide by 5685, doing that on my calculator, I've got 6,800 divided by 5685. I get 1.196 equals e to the 0.01279t. When in doubt, log it out. I'm going to log both sides. I've got the ln of 1.196 equals the ln of e raised to that power, which goes in front, 0.01279t. Agreed? The ln e is irrelevant. I'm trying to get t by itself, so I divide by 0.01279, divide by 0.01279, and t equals, so I'm hitting ln of 1.196, hit enter, divided by 0.01279. I get 13.99, which basically what? We can say, oh, it would take, now don't circle that even for the answer. So interpret what we just found, guys. The amount of time it would take for the population to reach 6,800 is 14 years. And the experiment started in 1995, didn't it? So it started in 95 with that many people. 14 years later, the population finally got up to 6,800. Oh, so if I take 1995 and I add 14 years to it, the population reached 6,800 in the year 2009. Wow, interesting. That's how you can use growth, decay, exponential equations, logarithms to make a prediction on a statistical study. Okay, so hopefully you find that kind of interesting. You learned a little bit. Guys, your homework, I'm not going to sit here and make you copy a bunch of these down. I attached this to Schoology so that you can call it up on your screen and take a look at it, or even print it out if you've got a printer and have the problems written there. So your homework, okay, for today, Tuesday, April 28th, so this is due tomorrow on Wednesday, April 29th at noon. That'll be our last day, by the way, finally, of this chapter on exponents and logs. And then we start our last chapter together on Thursday the 30th, okay? But the homework for tomorrow is 3 questions, very similar, mimicking what we did on the 3 that I just did. These, you don't have to rush through and copy down now from the notes because, again, I attached a document to your Schoology labeled 428 homework. So just go to that document, take a look at it or print it out, and those are your 3 problems for tomorrow, okay? Great job. We'll see you then.